Alright, so we're working this question. Alright, so given this question, to solve this question, we start off by finding out the reactions at the two supports. This is A, this is B, and that's point C. Starting off finding the reactions, since this is symmetrically loaded, the span from A to C is 4 meters, from C to B is 4 meters, 25 kilonewton point load, and 10 kilonewton per meter UDL. Looking at this from the point of view of these two loads being combined, it will produce a bending moment diagram that's going to be too complex to draw them combined. So I'm going to use this as an opportunity to explain how the principle of superposition also applies. So due to symmetrical loading in the first instance, RA, which is going to be equal to RB in this instance, is equal to half of 25 kilonewton. So this is looking at it as if it only has a point load of 25 kilonewton acting on it. That's going to be equal to 12 point, yeah, so that's 25 times half is 12.5 kilonewtons. So this is for the point load alone. If you look at the UDL alone, it would look something like this. RA is going to be equal to RB, which is going to be half of the 10 kilonewton per meter UDL times 8 meters span. That's going to give you 40 kilonewton. So that is for the UDL. Now if you were to combine these two, the calculation would have looked something like this. RA is equal to RB, which is equal to half of 25 kilonewton point load plus 10 kilonewton per meter times 8 meter right? And this gives you 52.5 kilonewtons. So that is if you were to combine the point load and the UDL. So combined, this is what it would give you. If you look at just the answers here, 12.5 and this 40, adding them up would have simply given you the same 52.5. So their effects combined give you the same thing. We can do the same type of calculation for the moments. Here you can see you have a pin support and a pin roller support. So because of those supports there, you can say that due to pin supports at A and B, the moment at A is equal to the moment at B, that's equal to 0, because no moments can develop there. Now the only other thing that you need to find out that's salient on this diagram is going to be the moment at point C. Again, you can calculate them separately and add up the moments to give you a combined moment with the effect of the point load and the UDL combined, the same way you did it for reactions. Now instead of looking at it combined, the M over EI diagrams for the point load and the UDL separately are going to be more useful to you. So let's look at those two calculations separately. So we'll only be looking at point loads and UDL calculations, no more combined calculation. So the moment at point C is going to be equal to the reaction, which in this case is equal for the point load alone to 12.5 kilonewtons. 12.5 kilonewtons times a distance away from C, which is 4 meters. That gives you 50 kilonewton meters. Alright, and this here is for the point load. And we can calculate the same way the moment at point C, considering only the UDL. So the reaction at A would be 40 kilonewton. Alright, so 40 kilonewtons times the same distance away, which is 4 meters, minus, because we're considering clockwise as positive about point C, that means this is positive as it was before, minus, because this is going in the counterclockwise direction around C, and the UDL is 10 kilonewton per meter, 10 kilonewton per meter, times a span of, so it's 10 kilonewton per meter times the span of 4 meters, times a distance from where it's centroid over this span from here to here, the centroid where all of this is acting. The centroid where all of this is acting is the midpoint here, right? So it's half of the span, that's half of 4. So that's going to be 4 meter over 2. And that gives us an answer of 80 kilonewton meter. And that is for the UDL. So drawing this bending moment diagram, we'll be drawing them separately, one for the point load, one for the UDL. And that would look like this. So those are the deflected, no, not the deflected shape, those are the bending moment diagrams. And the values that we have here, if we write them in, we can call them the M over EI value, since we have a constant EI. So for the point load, let's call this here point load and this one the UDL, and this one is for the point load. Alright, for simplicity and ease of calculation after, I can indicate that the centroid for this one is approximately there, for this one is approximately somewhere there, this one it's somewhere here, this one it's somewhere here. And the values for the point load, the maximum was this 50 kilonewton, so that's 50 kilonewton meter over EI, and this maximum value here was 80 kilonewton meter over EI. For simplicity, let's label these areas right away. This is area 1, area 2, area 3, and area 4. We'll need to find these areas, and we'll need to find the distances to the centroids. I've sent you guys a link on how to find the area of a half parabola and a parabolic spandrel. The distance from the centroid from this point to this point, or this point to this point of a triangle, and since the overall width is 4 meters as in the diagram, this is going to be 1/3 times 4 meter, and this side is going to be 2/3 times 4 meters. And for this figure here, it's going to be equal from here to here, and from there to there. This is going to be 3/8 times 4 meter, and this side is going to be 5/8 times 4 meters. That's the distance from the centroid. So finding the areas, in our case, for these diagrams here, area 1 is going to be equal to area 2. That's triangles half base by height, and for the half parabola, area 3 is going to be equal to area 4, which is 2/3 times b times h. So that is area 1 is equal to area 2 is equal to half times base times height. That's going to be equal to half times this width here is 4 meters, so it's the same 4 meters at the top here. 4 meters. So that's half times base, which is 4 meters. And in the case of the triangle belongs to the point load. So the height here is 50 kilonewton meter over EI. So that is 50 kilonewton meter over EI. That gives you an answer of, for simplicity, we say 1 over EI outside times 100 kilonewton meter squared, because meter times meter gives you the meter squared there. And let's do the same thing for area 3. It's equal to area 4, because there are two half parabolas. The area for that is going to be equal to 2/3 times base times height. Alright, and the base is 4 meters, the height is the 80 kilonewton meter over EI. So that becomes 2/3 times base times height, that's equal to 2 over 3 times the base, which is 4 meters, times the height, that is 80 kilonewton meter over EI. So that's 80 kilonewton meter over EI. So that works out to give you 1 over EI times, open bracket, 213 and a third kilonewton meter square. So now drawing the deflected shape will look like this. You have a point load in the middle and all of the little arrows for your UDL. It will have the deflected shape looking somewhat like this. Alright, so that's the deflected shape, and we need to find the delta C, and if we were to draw a tangent at point A, it will look something somewhat like this. Alright, so the tangent at A here shows you that theta A is that, delta C is this portion here. What we get from theorem 2 is this here, delta C A, where this is A, this is B, and this is C, this point here. And this height here we get from theorem number 2 as well, delta B A. So in order to find theta A, first we need to find delta BA. So let's take that using moment area theorem 2. Delta BA is found by taking moments of all areas between A and B so of the MOVI diagram, right? So that's going to be, that is area 1, comma area 2, comma area 3, comma area 4, about point B, this first one here, about point B of the M/EI diagram. So looking at this diagram here, that means that taking moments to give you the delta BA gives you delta BA is equal to area 1 plus area 2, that's these two here, area 1 and area 2, times what distance away is this overall centroid. Overall centroid is directly in the center, right? And from point B means this point here, this is point B, so the overall centroid is here, point B is here, so that's 4 meters away. So times 4 meters plus, and the same thing for the UDL, it works out to be area 3 plus area 4 together. Same thing, the overall centroid here is the center line here. The center line to point B is the same 4 meters. So in fact we can factor out the 4 meters. So this, substituting the values and factoring out 4 meters, works out to be 1/EI times, I think I need to open 2 brackets here, 100 for the first A, that's A1, plus 100 for A2, plus 213 and 1/3, that's for area 3, and the same thing for area 4, 213 1/3, right, kilonewton meter square. and we factored out the 4 meters, so multiply by 4 meters. This works out to give you 1 over EI times 2,506 and 2/3 kilonewton, and this is meter squared times a meter gives you now a meter cube. So that's your answer for delta BA. So now that we have delta BA, we can find, move this down. Now that we have delta BA from this big triangle, we can use the trig function of tan theta is equal to opposite over adjacent, and the adjacent here is the full length of 4 plus 4 is equal to 8 meters. But if you recall, using the law of small angles, the tan inverse can be ignored to give theta A is equal to opposite over adjacent, which works out to be opposite, that's delta BA, which we calculated just now to be equal to this, so that's 1 over EI times 2506 and 2/3 kilonewton meter cube, divided by adjacent, and in the diagram the adjacent of theta is the 8 meters. There's the 8 meters there. So all that divided by 8 meters, which works out to give you theta A is equal to 1 over EI times 313 and 1/3 kilonewton meter squared, because one of the meters cancels out. So that is the answer for theta A with the 1 over EI. If you were to substitute your values for E and I, you would get theta A working out to give you 313 and 1/3. Well, we need to convert this kilonewton meter squared to millimeter squared, so that works out to give you times 10 to the 6 kilonewton millimeter square divided by E and I, where in the question they gave us E as 210 kilonewton per millimeter square times 41,500 cm to the 4th. Converting that to mm to the 4th becomes times 10 to the 4th mm to the 4th, for the conversion for cm to the 4th power to mm to the 4th power, and that works out to give you 3.5953 times 10 to the minus 3 radians, which is the equivalent of 0.206 degrees. So that there is your answer for theta A. Now the second thing that I wanted to find was theta C, not theta B. So to find theta C, we need to use moment area theorem 1. So we can state that theta C is, we don't know what it is, using moment area theorem 1, we can find theta A minus theta C. That's what theorem 1 gives you. It gives you the difference between the angles at 2 points on the deflected shape. And after we have that, then we can find theta C, as we already know theta A. We just calculated that. So moment area theorem 1 states that the area of the M over EI diagram between A and C is equal to theta A minus theta C. That is, theta A minus theta C is equal to, if you look at this here, remember that the extreme left is A, this extreme right is B, and here is C. So everything between A and C, we have area 1 and area 3. So if you add these two areas together, that will give you theta A minus theta C. So basically that is area 1 plus area 3. So let's calculate that. That's 1 over EI open bracket. Area 1 was 100 kilonewton meter square, and area 3 was 213 and 1/3 kilonewton meter square. So that's basically 100 plus 213 and 1/3 kilonewton meter square, which works out to give you 1 over EI times 313 and 1/3 kilonewton meter square. But we already know theta A, but theta A is equal to 1 over EI times 313 and 1/3 kilonewton meter square. Remember, we found that before, theta is opposite over adjacent. This here, that gave us this value, and theta A minus theta C looks like it's the same number. So if we transpose this, theta A minus theta C is equal to this, we end up getting an equation that looks like this. Theta C is equal to 1 over EI, that's this here, times 313 1/3 kilonewton meter square minus 1 over EI times 313 and 1/3 kilonewton meter square, which equals to 0. So theta C is equal to 0. If you were to look at the deflected shape here, it would have been obvious if you draw a tangent at this point, it would have been perfectly horizontal. So theta C is obviously 0. So that's the second part of the question. Theta A is found, theta C is found. The last thing to find now is delta C. So this is the last thing that we need to find, delta C. To find delta C, we need to find, using the second moment area theorem, delta CA. And that's going to be found using this smaller triangle, similar to what we did with this larger triangle. So if I can just sketch that. So sketching that, it would look something like this. And this is the deflected shape I'm sketching here. Look like a curve, somewhat like that. And obviously drawing a tangent. This would have been the entire diagram up to here. Obviously we don't need to concern ourselves with all that anymore. It was looking something like this, where we had delta BA. But now we only need to look at this portion here. So this is the delta C that we need to find. And this here is delta CA. A. So this is point A, this is point C. We already know this angle, theta A. And the distance from here to here is 4 meters. So repeating the same rule of small angles, they're using the law of small angles, we find that this here, this side of the triangle is equal to this angle times 4 meters. So that's going to be these two added together. That's the height. Delta C plus delta CA is equal to theta A times 4 meters. Similar to what we did here, theta A is equal to opposite over adjacent. Now we have opposite, sorry, we have adjacent, we have theta A, so transposing it, opposite is what we need to find. So opposite becomes this. Theta A is still theta A, and adjacent is 4 meters now instead of 8 meters for when we were trying to find delta BA. And since we know theta A, substituting that in there, we get 1 over EI times 313 and a third kilonewton meters squared. So this here is theta A times 4 meters, which works out to give you 1 over EI times 1253 and a third kilonewton meter cube. So that is delta C plus delta CA is equal to this. But what we need to find now is just delta CA, so we can subtract that from this answer to give you what delta C is. So now we need to find just delta CA. So the same way we did it before, we can state that using moment area theorem 2, delta CA is found by taking moments of all areas between C and A, C and A. That is, if you look at the diagram, between C and A, we have A1 and A3. That is A1 and A3. About point C, on the M over EI diagram. So doing that, it's going to be area times distance. That is delta CA is equal to area 1 times the distance to point C. Alright, so this is area 1, the value is 100 kilonewton meter square, and the distance from this point to this point, I had put it here, so from this point to this point is the same thing, 1/3 of 4. And for area 3, it's this area times the distance from this center right to here, which is going to be 3/8 times 4, same thing to this side. So let's write that out. It's equal to, open bracket, 1 over EI times 100 kilonewton meter square times the distance 1/3 times 4 meters, so times 1 over 3 times 4 meters plus open bracket. Now we're dealing with A3, so that's going to be 1 over EI times 213 and a third kilonewton meter square. That's this area times this distance from here to here, which is 3/8 times 4 meters. So it's 3 over 8 times 4 meter. That works out to give you 1 over EI times 133 and a third plus 320 kilonewton meter cubed, or 1 over EI times 453 and a third kilonewton meter cube. So what we just found is that delta C plus CA, delta CA, sorry, is equal to this, but delta CA is equal to this. So if we substitute delta CA in here, we can find the unknown delta C. Alright, so we now know what this is, and we know what the total thing is. So if we pull out this, we'll be left with just the delta C. This implies that delta C is equal to delta C is equal to 1 over EI times 1253 and 1/3 kilonewton meter cube minus 1 over EI times 453 and 1/3 kilonewton meter cube, which is equal to 1 over EI times a nice round 800 kilonewton meter cube. And that's your answer for delta C. Obviously, we need to substitute the E and the I in here now, which works out to give you 800. Converting the meter cube to millimeter cube becomes times 10 to the 9th kilonewton millimeter cube, all divided by 210 kilonewton millimeter square, sorry, kilonewton per millimeter square, times 41,500 cm to the 4th power. Converting that to mm to the 4th power becomes times 10 to the 4th power mm to the 4th power. This mm square combines with this mm cube to give you mm to the 5th, and dividing by this, you'll be left back with millimeters. The kilonewtons and kilonewtons cancel out. Calculating this, you get an answer of 9.1796 millimeters. So that is the answer there. So your 3 answers calculated for the question. The question asked, what is theta A? We found theta A to be equal to 0.206 degrees, and the question asked, what is theta C? We found theta C is equal to 0, and the question asked, what is delta C? That's the deflection at point C, and the answer for that is 9.1796 millimeters. Alright.